because there are cases where we cannot use direct substitution because the whole thing is going to blow up. Notice here we have x approaches 1 and we try to use direct substitution, we're going to get a 0 right here. 1 minus 1 equals 0. So in this case, can't do that. And if we try to do direct substitution in the denominator, we'll find that we also get a 0. And that's a big clue. When you have a 0 over 0 situation, when using direct substitution, more than likely this denominator shares a common factor with this numerator. So let's see if we can do that. So let's apply the factoring shortcut of the difference of cubes. So when you factor that one, what you do is you put the cube of the first one minus a cube of the second one, and then multiply that with the square of the first one plus the first one times the second one, 1 times x, plus the square of the second one. So 1 times 1 equals 1. Yeah, I gotta remember these shortcuts. So when you have minus here, then you're gonna have a plus here, and if you have a plus here, you have minus here. That's your basic factoring shortcuts. So we divide this one by x minus 1, and yeah, indeed we share a common factor. So now it looks like we have ourselves another function that was buried inside here. So let's say we'll call this one a g of x. So now we have two functions. We had g of x was x cubed minus 1 over x minus 1, and now we found another function buried inside that one, and this one is x squared plus x plus 1. So these two functions actually look alike in the number line. So I mean, not in the number line, in a graph. If you graph them, you will find that g of x is going to look something like this. And you'll find that f of x is also going to look something like that. And well, these two are supposed to look alike. So let me see. Try to make them look alike. All right. The only difference is that you can see that this one doesn't work when x equals 1. You're going to have a not defined. So if we set x equals to 1 right there, right there, x equals 1. On this one, you're going to have a hole right there. So you're going to have a hole right there. Because f of x, I mean g of 1 is not defined right there. It is the denominator cannot be 0. On the other hand, this function looks just like it, but this one has no hole. This one's filled in because it has no denominator restrictions. So this one has a filled hole, a point there. So theorem 1.7 says that we have two functions that agree in all the points except one point, then the limit of this function equals the limit of this function. So they have the same limit, and the limit is right there. Alright, so what's the limit? Now on this one you can use direct substitution. So as x approaches 1, we have 1 squared plus 1 plus 1. That's equal to 3. So the limit is 3. That's how you find the limit. You cannot use the direct substitution here, but you can derive another function, this one, and then you can use direct substitution on that one, and you'll find that both of these have the same limit, because this one was derived from this one. And to prove it, we're gonna if you don't believe me, we're gonna graph these two functions. We're gonna go to desmos.com, and we're gonna the first function is y equals x cubed minus 1 divided by x minus 1. So we had that. And if we move our y values here, when we approach 1, see the hole right there? There's a hole right there. X equal 1 and y is undefined. Okay, now I'm going to do another function, which is the one that we derived, which was x squared. Y equals x squared plus x plus 1. And you can see this is actually the same. It's the same function, it's overlapped. And if we move our cursor over here, when x equals 1, our y value, our limit is 3. So to review, we have this function. We try to use direct substitution, and it blew up because on this one is not it's undefined when the denominator equals 0. And from this, by factoring, we found that we have another function buried inside this one. And when we derive that one by factoring, we find that it's actually the same curve, except that this one has no holes. So when you use direct substitution, you can find the limit of this one. And then, because this one was derived from this one, so the limit of both curves exist, even though the first one has a hole.